Okay, so our third paper is also a conference paper. It's called Jumping Further, Forward Jumps in Gravity-Reduced Immersive Virtual Environment by HyeongYeop, Kang, Geonsun Lee, Seok Kang, Ohung Kwon, JungHyun Choi, Ho-Jung Choi, JungHyun. And HyeongYeop is going to give the talk.
Thank you for your introduction. Good afternoon. Thank you very much for coming today. My name is HyeongYeop Kang, and I'm from Korea University. Today, the second Lee and I are going to present our work. Please enjoy our presentation. The gravitational acceleration on Earth is 9.8 meters per second squared. In contrast, the Moon's gravitational acceleration is 1/6 of the Earth's. To provide this, we lift the user with a cable-driven system as shown on the right. If 5/6 of the user's weight is offloaded, the user will have a sensation of being on a lunar surface. The cable system uses 4 wires, and one end is connected to a harness which fastens the user's body, and the other end is connected to a drum winch through pulley. And in our system, the user's body was tracked by an HMD and 2 wireless controllers and 3 trackers. And the track data was processed by a Unity engine and applied to a virtual avatar on the lunar surface, as shown on the movie. In theme park and science museums, there is a considerable demand for this kind of reduced gravity simulators. Now, suppose children jump in the simulator. The workspace of our system is cubic, and each side is 4 meters long. However, the safe jump distance is 1.5 meters, and the safe height is 0.8 meters. There are many reasons why the safe area should be reduced so much. For example, at the time of landing, the final velocity is not 0, and then the keys move ahead to the steel frame, and it would be a serious accident. In order to secure a sufficient wide safe area, the cable system must be made larger. Unfortunately, it takes more space and costs a lot more. So, we propose to reduce the physical cues of the jump in a way that the discrepancy from the visual cues provided through a HMD was not noticed by the user. Now, let's discuss about the forward jump. The forward jump follows the principle of a projectile motion. Its trajectory is determined by the initial velocity, which is decomposed into vertical and horizontal components. And if we ignore the air resistance, the horizontal velocity is a constant. In contrast, the vertical velocity decreases linearly due to the gravity. The forward jump trajectory is described in terms of height and distance, and the trajectory's height is determined only by the initial vertical velocity, whereas the distance is determined by the both horizontal and vertical velocities. Now, let's reduce the trajectory without users noticing. At the time of takeoff, the initial horizontal and vertical velocities are measured. Then, expected distance and height of the forward jump are immediately computed. If they exceed the safe range, the physical jump trajectory is reduced. Let's see an example. Suppose the user jumps forward. Then the system computes the user's trajectory to find that it goes over the safe distance of 1.5 meters. Then the trajectory is reduced to the safe 1.5 meters. In the same manner, if the jump goes over a safe height of 0.8 meters, the trajectory is reduced to the 1.8 meters, 0.8 meters, sorry. Their discrepancy should not be noticed by the user. Now, Geonsun will present the experiments conducted to see how much the physical cues can be manipulated without users noticing.
Hello, I'm the second author, Geonsun Lee, and I will be presenting the rest of the presentation. So our goal is to manipulate the physical trajectory in that the discrepancy from the visual trajectory is not noticed by the user. To this end, we need to identify the maximum allowable extent of manipulation. In the experiments, we tested the horizontal and vertical motion separately. Let's take a look at the horizontal motion first. If a user jumps 1.5 meters, the jump is manipulated by 1.2, 1.4, and so on to make 6 test jumps. For example, if a 1.8 meter jump is manipulated to 1.5 meter, it may not be noticed by the user. However, if a 3 meter long jump is reduced to 1.5 meters, it may be. So each of the subjects repeated the jump for 12 times, and after each jump, users were asked whether they were aware of the manipulation. Similarly, for the 0.8 meter high safe reference jump, the 1.2, 1.4 multiplication was done also, and the same test was repeated. Here, the discrepancy is between the visual and vestibular organs, and the vestibular organs are responding only to accelerations. Therefore, we computed the acceleration threshold for natural manipulation. Here, the acceleration thresholds are those that are applied to the driving cables. The horizontal and vertical thresholds that are identified turned out to be 1.37 meters second squared and 1.69 meter per second squared, respectively. Now, we are all aware that the visual cues over-dominate the other sensory cues. Exploiting such visual dominance, we would like to produce longer and higher jumps than the physical one. For example, a user may jump 1.5 meters, but a 2.5 meter long jump may be provided through an HMD. And if the user does not notice the visual vestibular discrepancy, we can imply that we successfully deceived the user's perception. The goal of experiment 2 was to identify the natural visual gains. And we also did this for vertical and horizontal directions separately. Now for the reference, for example, if we have a 1.5 meter jump, this was scaled by 7 factors. And each jumps were repeated 7 times, and after each jump, users were asked whether the jump was perceived as natural. Also, this was done by the 0.8 meter high jump. And the identified range for the horizontal and vertical visual gains were to be 0.92 to 1.58 and 0.75 to 1.69. With the findings in experiment 1 and 2, we conducted user tests to compare the user experiences. As shown here, the tests were done on an extraterrestrial metropolis, and the user's avatar was placed on the top of the building with distance and height indicators to guide users' jumps. we conducted 2 user tests based on this application. The first test was done to investigate the sense of presence between different jumps. 3 cases were tested. For case 1, the trajectory was manipulated, but in this case, the manipulation was done over the acceleration threshold, so it may be noticeable by the users. In case 2, the trajectory manipulation was done, but this time within the acceleration threshold, so it may not be noticed by the users. Now lastly, for case 3, the trajectory manipulation was within the acceleration threshold, and furthermore, we applied natural visual gains, and both were not noticeable by the user. In each case, participants made 5 consecutive jumps, and after they completed each case, they filled out a eye group presence questionnaire. Now here are the results of test 1. Case 1 showed the lowest scores in terms of presence, which is compatible with our expectations since the acceleration threshold was over what we have defined. And in contrast, case 2 and case 3 had no significantly different results in terms of presence. Now in test 2, we were to find the relation between the distance height of 4 jumps and user experiences. 3 cases were investigated. First, the standard one. And the higher one was where the standard height of 1 meter was extended to 1.5 meters. And the longer jump where the standard distance of 2 meters were extended to 3 meters. In each case, the participants also repeatedly jumped 5 times, and after that, they filled out an E²I questionnaire. We had some interesting findings for the E²I questionnaire results. The analysis showed that the higher had the lowest scores in terms of presence and enjoyment, whereas the longer had the highest scores on those factors. Also shown in the open-ended interview, participants pointed out that higher was the most difficult jump to make. Actually, 3 participants said that they had some anxiety when they had to land when conducting higher. On the other hand, participants chose longer as the most exciting among the 3. Now let me conclude our presentation. In order to provide free, unrestricted jumps in a fairly restricted workspace, we propose to manipulate the physical trajectory and optionally apply visual gain to the visual trajectory. For this, we define how much the physical trajectory can be manipulated and how much the visual gain can be applied without users noticing. And then we tested whether the trajectory manipulation and visual gains can be simultaneously provided, and therefore providing longer and further jumps. Finally, we also made some user tests to investigate whether the user experience differed depending on the significantly far and significantly high jumps. Thank you. That would be the end of our presentation. And on a side note, Dr. Kang is also seeking for jobs, and for me, I am seeking for a doctoral degree program. So if you guys are anywhere interested, you guys can always be welcome to contact us. Thank you.
Okay, so we have time for a few questions. Step up to the mic and state your name and affiliation. I can start. So, did you notice with the manipulation with visual gains and the vestibular visual mismatch, any loss of balance or subjects falling or anything along those lines once they landed?
Within the natural visual gain range, they never felt the kind of failed to balance, and over the range, maybe they suffer from the kind of thing. So we hire some helper in front of them, and we make them balance well after the experiment.
Okay.
So I have two short questions. The first one is, was it hard for the user to use this interaction device? So how long was the training to feel comfortable with this? And the second one is, did you notice some issues with the headset moving? Because if we are jumping, we would have some oscillations.
Uh-huh. The first question is the practice.
Oh, yeah.
Yeah, every subject practiced at least 30 minutes to familiar with the reduced gravity environment and our cable disturbance system. So they can jump very well. And in our paper, we also explain the pilot test related to that kind of topic. And the second issue is pardon? What?
Yeah, the headset. Did you notice some headset oscillation when the user are jumping?
Yeah, it is another problem for us. So we make the AC Viber provides a room scale mode. So we set up a little bit higher, and the oscillation we can get the oscillation error, refined oscillation error with the software program.
Okay, thank you very much.
Yeah.
All right, let's thank the speakers again.